Morning, everyone. Let's start. Let me share my screen. Today, we will continue to work on the Azambi language. I have already posted the tiny risk simulator on Canvas. You can download it and try to run it. Before you run the simulator, you need to install JDK. I have already posted a PDF in the zip file for you to guide you how to install the GDK. After you successfully have the GDK, you can run the simulator. So today we will talk about a more advanced assembly language like memory access. For example, we have load instruction and the store instruction. This load instruction means we read the data from this address to this register. This address is equal to the data in R2 register plus 10. This store instruction means I store the data from this address. I store the data in R1, a register, to this address. The address equals to R2, data in R2 plus 10. So this address and the address in load means a memory location, a main memory location. So we use base and offset addressing in this example. So it's a two address mode. We fetch the content of R2, add offset 10, and then perform the memory access. So here is a more detailed explanation of those two instructions. So first, we need to read the content of R2, and then plus a 10, and then access the memory here. Also, we need to do that in the same way. But the only difference is for the first one, we try to read some data from that address. For the second one, we try to write some data to that address. So here is some example of the memory and array of the Zambi code. First, we have a large integer array, which has 10 elements from 0 to 9. Second, we assign a value to the fourth element of the array, and then assign another value to the fifth element of the array. We add these two elements and assign the result to the sixth element of the array. So all the operation here happen on the element, on the memory array, on the consecutive array in the main memory. So they are not registers. So in order to use assembly language to implement this piece of code, first we need to move this value to a register and then store the data in the register to that memory array, which by these two assembly language, we actually implement this C code. We assign 5 to the 4th element in that array. So here we have a assumption, which is the base of the array is actually saved in the R0. This is the reason why here is R0. Why this is a 12? 12 is actually the each integer occupy 4 bytes, except that 0. We have a 1, 2, 3. 3 elements, so we use 3 multiply 4 plus the address of 0, R0 in the R0. So this is why we write a 12 and R0 here. For the next sentence, we assign the 5th element. We assign 8 to the 5th element. So we first move 8 to R2 and then store the content of R2 or the data of R2 to this address. So the so-called 16 is actually 4 multiply 4 plus R0. So we add the operand in R1 and R2 and store the data, the result in R3, and then store the content of R3 to a new address, which is the 6th element of the array. So please notice that the addition or any arithmetic operation can only happen on register. But the array is actually in the main memory. So clearly you need a store instruction to store the data back into the main memory. The next instruction is the branch. The branch is very easy, just a B and then a label. So we go to that label unconditionally. For example, this is one addition. After that, we go to this full label here. And this label is another addition instruction. The branch can be further breakdown into if this flag is a flags.e is a 1, we go to this foo. Or if this GT flag is 1, we go to foo. So we use these two instructions to distinguish them. This is a B equal. This is a B greater than. So based on different register, these so-called flag are registers. Based on the content of the register, of one register, we can decide whether we need to jump or not. This is only the example of a tiny risk. In the real machine, we have a lot of these jump instructions based on different the content of different registers. For example, if we want to implement this sentence, if R1 is greater than R2, we store the 4 in R3. Otherwise, we store 5 in R3. So we first compare R1 and R2 first. So if it's a greater than if R1 is greater than R2, then the register flag.gt will be 1. In that case, we use this sentence to jump to this label, GT label. And then we can move this 4 into the R3. If the flag.gt is not 1, then we continue to consecutively execute the instruction list. So we will move the 5 to R3. So if R1 is larger than R2, we do the jump. Otherwise, we just linearly execute the code. So it's a simple. So here is one example of we do a implementation of this function. You can try this piece of code in both your C compiler and the tiny RISC simulator. And if you are interested in, you can also, you can also try to implement this function in the tiny RISC simulator. I will post some homework for you to do some implementation, do some programming in the simulator. Next, we will talk about an immediate number, which is a constant. And the move instruction is very important instructions. So we can actually add some following modifiers into the instruction that has an immediate operand. So the default move will treat 16 immediate or 16 constant as a signed number. And then we will do the automatic sign extension. We also have 2 alternatives. The first one is a move U, which treat the 16 immediate as an unsigned number. So you can recall the content we presented in the binary and the representations slide. So the signed and unsigned number have a totally different encoding or representations. The other alternative is the move H. Move H means left shift the 16-bit immediate by 16 positions. So it will not give you the unsigned or signed number. It just give you left shift 16 immediate by left shift the 16-bit immediate by 16 positions. I will explain why this instruction is helpful. So in the current CPU, they will convert the 16-bit immediate to 32-bit number. So it uses this 32-bit number for all the computations. And this is true for both the arithmetic and the logic instructions. We can use different methods to generate this 16-bit number. We can use different methods to convert this 16 immediate number to the 32-bit number here. The first one is a sign extension. This is default. Second one is we treat the 16-bit as an unsigned number. And then we can load the 16 in the upper bits. So this is the difference between U and R, and without any modifiers. So here is the more detailed explanation of these three different types of move. The first one is just you insert signed bits here. So when you see this symbol, it's a hex format, and this is a decimal 10 hex A here. So each hex can be translated to 4 bits. So if it's a decimal 10, it's a 1 0 1 0. Then the most significant bit of this number is 1. The most significant bit is actually 1. The sign bit is actually the most significant bit, and it's 1. So we will insert a lot of 1 here. If we treat this guy as an unsigned number, so we do not care about the signed bit, whether the signed bit is 1 or not, we just directly insert 0, all zeros here. For the last case, we just copy the data in the upper bits here, like this. Actually, the data is initialized at 10. So, but these are not necessarily 10 because you can add more content to this area. You can move some data in this area or add some data in this area because they are in the lower bytes. So it's easier for you to do the addition. Then if you use different move here, you will get different results. So here is one example. So if you use this move H first, it will copy this guy to the upper bits like this. And then you can add a value here, A9 2D to the lower bits of that data. So in this case, the addition, the operand of the addition will occupy this part. So this is the, how can you set this number into this register? You first do a move H instruction and then do an addition. Next, we will cover the functions. The function is actually another piece of code. The functions are the blocks of assembly instructions that can be repeatedly invoked to perform certain actions, operations. Every function has a starting address in the memory. So this is the starting address of the function foo. The address is A. So by calling a function, we need to assign the starting address to the program counter. The PC indicates a program counter. So in that way, the next instruction will start from that particular function, which is starting from A. We also need to store the location of the PC that we need to come back after this execution of this function. This is so-called return address. In this way, we can call any function and execute their instructions and then return the saved return address. So here is one example. So the caller is for example, your main function. You write a main function like this. In your main function, you can call another function. And then you go to that particular or specific function you called. That is a so-called callee. Your main function is the caller. You execute it. So in this way, you assign the PC to this address, I don't know. Let's call this address as A. UPC equals to A, and then your code will go to this address and then consecutively execute the instructions here until it reached the return instruction, and then it will come back. And this instruction has the address of P4 plus, P plus 4. This instruction has the P. But here you may execute maybe 1 million instructions. But the address when you call the function is P, and the return address is only P plus 4. So here there is only 4 plus 4, 4 offset. But here you can have millions or billions instructions. So we assume that each instruction takes 4 bytes. This is the reason why we plus a 4 here. But here you may have billions of 4 bytes. So how can we, store the return address? And how can we, when you are in the main function, when you execute some instructions in the main function, you may occupy several registers, register 1, 2, or 3. But if you jump to a new function, in that particular function, it will also use the R1, R2, R3. It will cover the old content in your R1, R2, R3. After you finish this function, when you go back to your main function, or when you go back to your caller function, you will find out that your old data are covered by the function you called. You may have some errors in that case. So you also need to store the value or the data in those registers before you call the callee function. So in that way, you can also recover those values in the R1, R2, R3 function. For example, you have a main function here. You try to run your code like this. And in the middle of the instructions, in the middle of the function, you will call this full function. But before that, you also use the R0. You move some data in the R0. You also move some data in the R1. So these registers are occupied. Again, when you try to call the full function, when you go to the full function also will have some operation on those the same registers. It will easily cover you all the data. In this way, you need to do some protection. You need to store the content of these register before you call that full function. But after the execution of your function, you will go back to the main function here. So you only have a limited number of registers. And you will use those registers in both the caller and the colleague. You may also need those registers to pass some parameters from the main function to your colleague function. The solution is, of course, use some memory, main memory. Because you have a limited number of registers, you also need may overwrite the register when you try to recursive call some function itself. So this is so-called a register splitting. So I will explain the details of this function. So the caller will save a set of register before call the function, and then it will call that function. After the execution of the function, the caller will restore the registers. This is so-called caller saved scheme. The caller saved scheme means the caller will take care of the content in the registers. There is another scheme named the colleague caller scheme. So the caller will not save the set of the content of a set of a register, but the colleague will do that. When before the colleague overwrite anything, the colleague will save those register file content of those register files, and after the execution of the colleague will actively recover the data before run the return address. So this is the difference. You will save the content of the register anyway. This is so-called register splitting. Either the caller will do that. The caller will save the data and then restore the data without bothering the colleague. So you can see the colleague did nothing. It has nothing to do with the splitting. But the same job can be also done by the colleague. So after the PC get into the colleague can save the register files and then restore the register files. And the register file content will be stored in the main memory. You will need those load and store instructions to do that. So before you do anything, you need a restrict agreement between the caller and the colleague regarding the set of the memory location that need to be used. Because you need to protect that memory region. Otherwise, some other instructions or some other application may also overwrite that part of region. So that's not good. So you need to dedicatedly allocate a piece of memory region for that use or for that register splitting. And after the function is finished, that region needs to be reclaimed. Otherwise, you always allocate a new array. You never reclaim any used array. In that way, your memory will use up very soon. So each function will be translated to an active block. It has some arguments and return address and some area to store the register content. So the register spell area and also some local variables. So the active block is actually a memory map of the function. So you keep all the necessary variables, register data in that active blocks. Of course, the active block is in the main memory. So this is the arguments, the parameter you can pass to this function. From this parameter or these arguments is actually passed from the caller to the colleague. And then these are the local variables. The address of this return is also will be stored in this return address. So generally, we can assume the caller will do the register store and recovery. This so-called caller saved splitting. before calling any function, we spill the registers, and then we allocate the active block for the callee. We write the parameters we want to pass to the active block if they cannot fit into the register. We of course have some dedicated of register to do the argument passing, and then we can call the functions. So in the call the function, first we need to read the parameter or the arguments. Second, we need to save the return address. And then we allocate a space for all the local variables. And then we can execute the functions. Because this active block is actually allocated by caller, it will assign a limited space for this local variable. So you cannot allocate a very large memory like this. If you want to allocate a very large memory in the function, you have to use the heap. You have to clearly use the malloc function and use a free function to allocate a array and reclaim a used array respectively. So that's the concept of the heap. And of course, you have to use C or C++ in order to understand all these memory management. You can see that memory management is heavily related to the assembly language or the low-level programming language. Once the function completes, you can restore the value of the return address register and write the return values to the register, and then destroy the activation function. And then you can do the return. You return to the caller. The caller will retrieve the return results, the value you returned, and then restore the spilled register, and then continue to the next instructions. So all the information of an executing function is actually in the activation block. These blocks need to be dynamically created and destroyed millions of times. So which means that when you try to call a function, you also introduce some overhead. But again, for today's state-of-the-art machines, these overheads are trivial. And then we will talk about how to manage the activation block, how to the faster creation and the deletion of the activation blocks. So this is a main function. In the main function, we will call another two functions. The other two functions, which is a test. In the test, we call another function means test2. After the execution of the test2, we return to the test. And then we return to the main. We call another function means foo. In the foo function, we call a function named foo bar. And then call a function named foo bar bar. After execution of this one, we return to the foo bar, and then return to the foo, and then return to the main. So this is actually the typical structure of a stack, which we have the last in and the first out. The so-called last in means the foo bar bar is the last function we get into the structure, but it will go out first. out of this structure first. So this is the so-called stack. Here is the details of the stack. A, B, C, D indicate the time step. So at beginning, we only have a full function. And then we call the full bar. And then we call the full bar. This is the time step. And this is the the height of the stack. So the full bar is the last one to get into this stack, but it go out of this stack at the first. And for the stack, you only have the limited capacity for the stack. So if you want to allocate a huge memory, you have to use heap. So we typically allocate a part of the main memory to save the stack, and the stack are downward growing. So the first activation block starts at the highest address, and the following activation blocks are allocated to the lower address. So we have a so-called stack pointer, which is a SP, to point at the beginning of a activation block. So this is how we allocate a activation block. This is so-called deallocate activation block. So please notice that the first activation block is actually started at the highest address. So when I add a constant to this stack pointer, I'm deallocating. I'm pop out some content, some activation block out of the stack. So when we subtract some constant, I actually pushed more activation block into the stack. So please notice the difference between these two. And the stack is, of course, will be managed by your software, by your compiler and your operating system. So we have a register to store the return address. When we try to call a function, we just store this PC+4 in the RA, and then we go to that particular function. So just the so-called RET return instruction means we just put the RA back to the PC so that the next address will be the RA. And here is one example. So when we try to call a function, we put the next instruction address of this current address to the RA, and then we go to this function. After the execution of this function, we restore the RA to the PC. And this is the C code of this example, and you can check the assembly language code. So in the assembly language code, we have this the whole process. For example, we move 10. 10 is the argument here. We move 10 to this R0. So the R0 can help you pass the arguments. And then we call this function. So at the beginning of this function, we directly can use the content in R0 because we pass this 10 through this R0. Now we have a 10 in the R0. And then we also have the code to maintain that stack. So please read this piece of code after this lecture. We also have some instruction means do nothing. Do not NOP instruction can help you to do some synchronization. If you do the programming on multiple core, if some core finish some job earlier than other cores, then these core need to wait for the slow core. In this case, you can use this NOP operation. So because this is RISC instruction set, the length of each instruction are the same in the RISC instruction. So each instruction will be encoded by 32 bits, I'm sorry. We have 21 instructions. So we use 5 bits to do the encoding. The 5 bits indicate the instructions. For example, the addition is encoded as all zeros here. By looking up this table, you can know what instruction you are executing. So the format of each instruction will be encoded like this. This 5 bits is opcode, and the rest includes the register name, the constant, the immediate number. You can encode everything, all the other things by this 27 bits. So the NOP and the retire operation has no other area. It only needs a opcode. So the opcode of this guy is here, and the opcode is yes, here. So they only have one opcode. They do not have the rest of the instructions. So these are two very simple ones. But the general structure of the instruction encoding is something like this. So this is the so-called one address instruction. One address instruction has the branch instruction, call instruction, not instruction. So I will use branch as one example. And opcode is also 5 bits. The other 27 bits can be used as offset. The offset will point to a 4-byte word. The actual address is computed like this, which means that this 27 bits are enough for the offset encoding. And then we have 3 addressed instructions, which is all these. We have 3 operand, we have 3 fields of this for these instructions, 2 operands, and 1 is the result register. So these 2 are the operands, and this one is the result. we use 1 bit to indicate whether the second one is a register or immediate. So if it's a 0, then the second one is a register. If it's a 1, then the second one is an immediate number. Since we have 14 registers, so we need 4 bits to specify a register. By 4 bits, we can address this 16 register. For example, the 00040 indicates R0. So the structure of the 3-addressed instruction can be like this. So we have the first operand, the second operand, and the results. The first operand can be also called source register 1. The second operand can be called source register 2. The result can be called destination register. And this bit indicates whether the second one is a register or an immediate number. And you can see that these bits can be easily fit into the 27 bits. So the total length of the instruction is 32 bits. This 32 also means when we talk about the machine, we have 32 bits machine or 64 bits machine. This 32 bits can also indicate, okay, the tiny RISC is a 32-bit machine. And of course, everyone knows 32-bit machine is less powerful than the 64-bit machine. Why? Because apparently 64-bit machine can have more operand, can have more register files, because each instruction of a 64-bit machine can encode more content. That's the reason why 64 is more powerful. If this one instruction has only a limited length of bits, which is a 32, it only can encode a limited number of register files. As we all know that the addition, multiplication, parameter pathing, all these functions happen between the register files. So in this way, the more register file we have, the better performance we can potentially achieve. So this is good. We prefer more register files, but we only have a limited length of each instruction, which means that by this 32 bits, at the most, if I use all these 27 to index register, this is the total number of register I can index or I can addressing. So this is the upper bound. Even you give me a limited number of register, I cannot use them. So this is the difficulty. And we also have some modifier bits like the U, the H, I presented in the previous slides about the move instruction, move U, move H. And these two use 2 bits, and all the other bits, and sometimes these 2 bits can be used to encode immediate number. The immediate number occupy 18 bits. Again, the same issue can also happen on the immediate number. Can you encode 10 to 256? I'm afraid not. You cannot do that because you only have 18 bits here. In the best case, you can index this number. This is the largest number you can index. If you want to index this number, that's impossible. And for some two-addressed instruction or one-addressed instruction, they will only use maybe 2 fields here. So they are a subset of the 3-addressed instruction. So these are the details for these 2-addressed instructions. Some part is not used. These 4 bits are not used. And this is the load instruction and the store instruction. They are also 2-addressed instructions. These are their instruction encoding. And also, when you use the load, when you use the store, you need to encode your memory address, the memory address you want to read your data, and the memory address you want to write your data into the instructions. Again, you only have a limited bits for them. So if I give you, let's say, one petabytes data, you cannot address them. Petabytes may be millions of terabytes. And this is the store instruction. It has 2 register sources, but no destination register. And it also have 1 immediate field. But it cannot fit into the immediate field because the second operand can be either a register or a immediate number, but not both. Should we define a new format for the instructions? We don't need to do that. So we can make an exception and use the immediate format to do the encoding. We can use the RD field to save one of the source register, like this. So this RS can be encoded here, and this immediate can be encoded here. So these 3 this table is a summary of the encoding of the instructions. We will cover the branch format, the register format, and the immediate number format. So you can see for the immediate number, you only have 18 bits. For the register, you only have 4 bits. And for the offset, you only have 27 bits. These are limitations. Any questions? If no question, we can stop today. I will post some programming problem on Canvas. My plan is to use the tiny risk to implement a sorting algorithm. For example, an insertion sort problem by the assembly language. If no question, we can stop today. Thank you very much.
I have
Okay.
a couple
Yes.
questions.
Yes.
So first, the thing you emailed us yesterday with the tiny risk, it only has the Windows installation like instructions. Is it okay to install it on like Linux or Mac?
That's okay.
Oh yeah. And then for these 32-bit instructions, how do you like I see that if you have like values already in a register, you can like load them with only the 4 bits to like tell which register, but how do you like initially put like a 8-byte pointer or something into a register with only like 32 bits?
First, you can move some value to the register if you want to initialize the register. So this is the move instruction. You can use the move instruction to move some immediate number to the register. So here is the register name. And for the move, of course, you can move 18 bits data. If you want to do the 4 bytes, how can you do that? I think I explained this. I would like to remind you that you have the move age instruction.
Oh yeah. So you do like 16 bits at a time.
That's right. That's right.
Okay.
Yeah, this is the solution. So you first move the upper bytes data to the upper bytes and then add another lower bytes data.
Okay, that makes sense.
Okay.
Thanks.
Any other questions? If no question, we can stop today. Thank you very much.